So, what Kepler was actually after was this third law. Okay, so this is the end game. So, Kepler had this goal that there should be a simple mathematical relationship that relates the orbital period of a planet to how far away it is from the sun. So, this is the only time I will ever say this in this class. It is the only time. Because this is a ratio, it doesn't make any difference what orbit or what the period is in. Doesn't matter. Could be days, could be years, could be hours, could be seconds. Doesn't matter. Because it's a ratio. Okay? Same thing with radius. The radius could be in inches, millimeters, astronomical units, miles, light years. Don't care. Okay? They just have to be in the same units because it's ratio. I will never say this again in the history of this class, that the units don't matter. Okay? They don't. Because it's ratio. Now, so let's see how this plays out. So the other thing that you have to understand, and this is going to be important once we get into Newton's laws, is that this is only valid for objects that orbit the same center. Like we could compare Earth and Mars because they both orbit the sun. But we could not compare our moon, which orbits the Earth, to a Galilean moon, which orbits Jupiter. Okay? Because that's orbiting Jupiter, even though they're both moons, like Io, Calypso, whatever. Okay? You got those moons that are orbiting Jupiter, you have our moon, which is orbiting our rock. I could not use Kepler's laws on them because they don't orbit the same center. Okay? It works great, it's beautiful, but there's limitations to what you can do. So let me give you a simple example how this would play out. So let's say that you know that you see a news flash come across your phone. Planet X has been discovered and it has a radius of 4.80 AUs. Okay? So they spotted it, got a new planet. 4.80 astronomical unit, that's its radius. So what we want to figure out is how long is it going to take for planet X to go around the sun. Okay? So understand what the 4.80 is. The 4.80 is not how far it is from the Earth. It's how far it is from the sun. So what that means is this planet is 4.8 times further from the sun than the Earth is. Okay? So for Kepler's laws to work, you need 4 variables. You need the period of planet X, the period of Earth, the radius of planet X, and the radius of planet Earth. Okay? I need 4 variables. So, you've got the radius of planet X, 4.80 AUs. Let's talk about the orbital radius of Earth. If you're Kepler, what are you going to let the orbital radius of Earth be? 1 AU, right? Cool, that's that. We're trying to find the period of planet X. Now, before you do any math, let's think this through. We're saying here's the sun, here's the Earth, here's planet X. Okay? So is the period of planet X going to be bigger or smaller than the period of the Earth? Bigger, because it's further out. Farther out you go, the longer it takes to go around, which is why Mercury is so fast, because it orbits so close to the sun. Okay? So there's a couple of options on the period of the Earth. We could let it be 365 days. That's an option. Or we could let it be 1 year.
1 year. 1 year.
1 year. Why?
It's because one's easy simple.
One's easy to work with. Your Kepler's like, oh man, come on. I just got back. I've loved 15 volumes of books. I've stormed a castle. Really? I don't have a calculator. I don't have Oreos. Come on, throw me a bone. So it goes, okay. We're going to let that be 1 year. Okay? So what we don't know is the period of planet X. Now, what would be the simplest possible ratio between orbital radius and period?
1 to 1.
1 to 1. The simplest possible ratio would be a 1-to-1 ratio. If planet X is 4.8 times farther, what would the period of planet X be? 4.8 years. That would be the simplest possible ratio, a 1-to-1 ratio. Planet's twice as far, hey, it's going to take 2 years to orbit. 3 times out, it's going to take 3 years to orbit. That would be the simplest possible ratio. Yeah, it's not going to happen. It's close though, but it's not bad. So, what you have is this. Period of A squared, radius cubed. Now, you know how I feel about fractions. I hate them. So I'm going to cross multiply because I don't like fractions. Okay, even as ratios, I don't like them. So I'm going to take the period of A squared times radius of B cubed, radius of A cubed times the period of B squared. So this is going to start as the period of X squared, period of Earth squared, equal the radius of X cubed and the radius of Earth cubed. It doesn't make any difference which one you put on top or bottom. They just have to be the same. I can't put period of X up here and then put the radius of Earth on the other side. Okay? It doesn't make any difference because it's a ratio. But just make sure that they're on the same side. Now, I'm going to cross multiply. So I'm going to have the period of X squared times the radius of Earth cubed is going to equal the period of Earth squared times the radius of X cubed. Nice. Now, your Kepler. What did you let the radius of Earth equal?
1.
That's just 1. What did you let the period of the Earth equal?
1.
1. So what are you left with?
Tx squared equals
Tx squared equals
RX cubed.
Rx cubed. Right? So it looks horribly daunting, but it simplifies down to this. Now, word of caution. Listen to me. Listen to me. That was a cool trick. But that only works if you let the other values have numeric values of 1. Okay? So like if you had let the period of the Earth be 365 days, this won't work. Okay? If you let the radius of the Earth actually be that numeric distance from the sun to the Earth, can't do it. Okay? So it only works if you're dealing where you have one of the planets has a period and radius of equal to 1. And if you're not sure, do the full Monty, okay? Write the whole thing out. So in this situation now, remember, you're Kepler. So what you've got to do is you've got to take the square root by hand, square root of 4.80 cubed. Okay? So now, y'all have the benefits of calculators. So somebody cube 4.8, and then take the square root of it.
10.52.
What'd you get?
10.52.
10.52? So 10 and a half, in this situation, years. Okay? So if you're going to have birthdays, don't go to planet X. Because you're only going to have a birthday if you define a birthday as being one lap around the sun. You're only going to have a birthday every 10 and a half years.
that sucks.
But the cool thing is the drinking age is like 2.
Yeah, that's correct.
So how old do you have to be to drink? 2?
Yay!
Problem, it takes a long time to get.
Yeah, you want to
Okay. So now let's talk the perspective of the scientific community at this point. So this is early 1600s, early to mid 1600s. Kepler's come out, they've accepted the Copernican system, a heliocentric model. Kepler embraced the Copernican system. He steals the data from Tycho Brahe. publishes his work. Cool, everybody's happy. But they don't understand the mechanism at this point. They know it works, and even Kepler said, look, dude, I'm just like the reporter. Okay, I figured out the news story, I figured out the equation. Why it works, not my deal. That was not in the contract that I signed with God. My goal was to find the equation, not to explain why it works. So, to understand why it works, now we got to roll this into Isaac Newton. So one of the equations that Isaac Newton came up with is this. F equals big G, M1, M2, over D squared. If you're talking an orbital radius, it's the pirate thing, would it be over R squared. So this big G is called the constant of proportionality. So big G has a value of 6.67 times 10 to the negative 11 newtons meters squared over kilograms squared. We're going to be dealing in this unit more than about any other unit with some very big numbers that are constants. If I were you all, I would get in the habit of storing these numbers in your calculator, because that way you don't have to punch them in every time, okay? If it's any kind of TI, it's going to have an STO function, and then you assign it to a letter, okay? So if you're not sure how to do that, check with somebody. This is the first number that you really need to store, is that universal gravitational constant. So, I'll explain tomorrow, but Newton actually didn't come up with the numeric value. Just like Avogadro didn't come up with his own number, Avogadro just proposed the idea, okay? Avogadro's number was actually found by someone else. Newton just said, hey, here's the constant of proportionality. I got other things to do, I'm out. Deuces. You guys figure it out. So let's do something simple, okay? Let's do something simple. So Ava is now Ava, she's no longer the sun, okay? So Ava is here, and let's say Ava has a mass of 50 kilograms, okay? Over here, there's a fire extinguisher on the wall, and that has a mass of 2 kilograms, okay? And Ava and this fire extinguisher, that could be the name of her band, give it up for Ava and the fire extinguisher. Thank you very much. And they are separated by 5 meters. So what I want to do is calculate the gravitational attraction between Ava and that fire extinguisher, okay? Got it, good, great. Now, initially, do not touch a calculator, step away from the calculator, do not touch a calculator. So we're going to take 6.67 times 10 to the minus 11 newtons meters squared over kilograms squared times 50 kilograms times 2 kilograms divided by 5 meters squared. Now, this is why the gravitational constant has this weird jacked up units, okay? So it's newtons meters squared over kilograms squared. So when I multiply kilograms by kilograms, I get what? Kilograms squared.
Cancel.
Those cancel out. Then I divide by meters squared. That cancels those out. What do I have left? Which is a measure of force. Okay, cool. Now, step away from the calculators. Do not touch the calculator. One of the things that I'm going to preach to you, and in this unit, more than about any other unit we will do, because we're dealing with such big numbers and squared and cubes and things like that, this unit has the potential, more so than any other unit, for you to get answers that make absolutely no sense at all, and off by a long shot in terms of this makes no sense. So, for example, one of the things you're going to do, it's a classic fixes problem, is that you had the lunar command module that was orbiting the moon. And you have to figure out, and we're gonna calculate how long it takes for the lunar command module to orbit the moon. Should take about 90 minutes, about an hour and a half, okay? Here's the extreme answers that I've gotten over the years for this calculation. One answer I got was about like 0.05 seconds. Okay? That's less time than it takes to snap your fingers. Like, you can't snap your fingers in 0.05 seconds. Like, you're gonna go all the way around the moon in less time it takes to snap your fingers. Let's think about that for just a second. Now, the other answer I got, this is a massive number, massive. And I actually did the conversion. And if I took that answer in seconds and converted it into years, it was actually longer than the universe itself has existed. No, it's a true story. It was bigger than 14.7 billion years. Okay? It's like the universe itself has not existed this long.
And they gave you that answer?
Oh, absolutely. And I said, what happened? Well, the calculator said that was the answer. It didn't seem right, but that's what I got. So the oracle will absolutely lie to you on this unit, okay? Absolutely. But if you get in this habit of doing what we call order of magnitude just gets you like a ballpark idea of what it should be, okay? So if I take 50 times 2, I get what? 100. So that's 10 to the second, right? 100 is 10 to the second. True?
Sure. Yeah.
And then I'm going to multiply that by 10 to the 11th. So if I don't care about what the actual numbers are. All I'm doing is the order of magnitude. Okay? 10 to the negative 11th times 10 to the second gets me what?
10 to the negative 9.
10 to the negative 9. 5 squared is,
25.
which is 10 to the first, right? So if I take 10 to the negative 9th and divide that by 10 to the first, I should get 10 to the negative 10th. So my order of magnitude, as a ballpark, just a ballpark, should be around something 10 to the negative 10th. So if I do this, if I get like 10 to the 14th, oh, I've done something really, really wrong, okay? Or if I get 10 to the negative 20th, I've done something really, really wrong. So the order of magnitude just tells you, is like, am I even close to what I should get? Okay? We're going to do this a lot, so we get used to it. Now, somebody actually crunched the numbers. Tell me what you get.
2.668 times 10 to the negative 10th.
So 2.7 times 10 to the negative 10th. Okay? Newtons. So when I'm up here lecturing, there's a lot of things that I worry about. One of them, what I don't worry about is all of a sudden Ava starts being accelerated towards the fire extinguisher. Okay? Is there a force between Ava and the fire extinguisher?
Yeah.
Yes,
It probably is.
there is. Is it enough to make any difference? No. Okay, not enough to make any difference. But now, let's say Ava goes, I feel that. Okay? This is bad. I don't want to feel that force as much. So if Ava wants to decrease the gravitational force between her and the fire extinguisher, what's she going to do? Get closer or move further away?
Further away.
Further away. So let's say she doubles the distance
10.
from 5 to 10. Okay? From 5 to 10. Now, this is relatively simple. What's 10 squared? 100. What's 50 times 2? 100. So what's the answer if she moves 10 meters away?
6.67
Oh, 6.67 times 10 to the negative 11th newtons. Okay? Now, somebody take the 2.7 times 10 to the negative 10th and divide that by 6.67 times 10 to the negative 11. What do you get?
4.
4. Coincidence?
No, I think not.
I think not. So if she doubles the distance between her and the fire extinguisher, is the force 4 times greater or 1/4 as much?
1/4 as much.
1/4 as much, so this is an inverse square function. So every time you double the distance, the force goes down by a factor of 4. Now, but the bell is gonna ring. Ava's going, Miss Burkamp, love you to death, but I gotta go. So she's gonna get up and she's gonna walk towards the fire extinguisher. At some point, she's gonna be 2.5 meters away. If she reduces the distance by a half, then what's gonna happen?
4 times greater.
Then it's gonna go up by a factor of 4. Okay? So doubling, tripling the distance has a great impact on the force. Okay? Now, we won't actually do this computation. But now that you get the idea. So I want to find the gravitational attraction between Ava and the Earth. Okay? There's 3 ways we can do this. Let's talk about the first way. And the right index finger of Ava's hand, there's a strand of DNA. And inside the strand of that DNA, there's a nitrogen atom. And inside that nitrogen atom, there's a proton. Okay? So there's that proton. So that proton, because it has mass, is gravitationally attracted to every particle that makes up the Earth. Okay? So what we're going to do is we're going to go F equals big G, mass of that proton, mass of something else divided by distance squared. So we're going to have to know the mass of that proton, and we're going to have to know the mass of and location of every particle that makes up the Earth. Every proton, electron, and neutron that makes up the Earth. And we're going to do this computation again and again and again and again and again between every particle. And that's just for one nitrogen atom. And that's just for one proton. Oh, there's a neutron. Guess what we're going to have to do? Exact same thing. Does it seem reasonable at all to do it this way?
No.
No, it's horrible. But here's what's important, that you understand that's what creates the gravitational field, is that every particle that makes up Ava and you is gravitationally attracted to every particle that makes up the Earth.
Oh.
Now, you're going, that's not cool, because there's a better way. Sure there is. We're going to treat Ava as a point mass. So imagine that we're going to take Ava and we're going to crunch her down, okay, until she's like the size of like a garden peak, okay? So this is Ava, boom, garden peak, right there, Ava. Then we're going to do the same thing with the Earth. We're going to take the entire Earth, and we're going to crunch the Earth down until it's one point mass, okay? Not a bunch of protons, electrons, and neutrons, but one single point. Now, this is another number that you'll need. I'll give it to you later. Mass of the Earth is 5.979 times 10 to the 24th kilograms. The average radius of the Earth is 6.3713 times 10 to the 6th meters. Okay? That's how far apart they are. So imagine that you have 2 points. You guys got to go?
Yeah.
Okay, we'll finish this up tomorrow. No, you don't have any homework. But enjoy the